Hello and welcome to this lecture on Monte Carlo simulations. In the last lecture, we considered several details of molecular dynamics. Not only we discussed the algorithms, we also defined what are pair correlation functions, that is the radial distribution function as well as the time correlation function. So, this time we will do what are called Monte Carlo simulations, and Monte Carlo simulation really mean simulations which use lot of random numbers in the simulation algorithm. So, they will not use equations of motion, they will just use random numbers to move all the particles based on an algorithm, and the term Monte Carlo came because of the casinos in Monte Carlo, but they could have also been called as a Las Vegas or any other name. So, the correct name would be Metropolis Monte Carlo, because it was Metropolis and others who gave that algorithm. So, another name for Monte Carlo simulation could also be stochastic simulation. Stochastic means any process that uses random numbers. So, what are these simulations now, or what are the uses? There are many types of Monte Carlos. Okay. So, this kinetic Monte Carlo can be used to simulate an activated process, okay, or a process which occurs with an exponential probability. An activated process occurs with a probability of e to the minus energy by kT. So, this is an activated process. So, there is also what is quantum Monte Carlo that can be used to calculate electronic structure. Okay. Now, there is also what is called diffusional Monte Carlo. It solves this time dependent Schrodinger equation, but we are not interested in all this. Okay, shuru karu? Haan. So, our interest is in the liquid state simulations. So, what we do? We will just consider classical liquids and how to simulate the structure of that liquid. So, Monte Carlo simulation uses random numbers. So, therefore, they will not tell me anything which is a function of time. So, they will only give me the structure or the equilibrium distribution function. Okay. So, let us see what is the strategy here. So, this particular Metropolis Monte Carlo, you can see that paper in Journal of Chemical Physics volume 21 1087 1953, a very remarkable paper. Okay. So, their aim was to calculate the average energy of the system by moving all particles randomly. Okay. The strategy is take a set of configurations, move particles randomly and see whether after you move the particle, the new move is acceptable or not. So, okay. So, once you find out whether the new move is acceptable or not, so for each step you will have physical quantities like Helmholtz free energy or internal energy, or every physical quantity will have a value at each step. When you average over the entire configuration and divide by the number of steps, you will get the average value for that. Okay. So, this Metropolis Monte Carlo follows the NVT ensemble, that is the number of particles is fixed, volume is fixed and the entire calculation is done at a fixed temperature. Okay. So, the Monte Carlo simulations correspond to NVT calculations, whereas the molecular dynamics correspond to NVE, that is a different ensemble, because normally temperature should not be fixed in a molecular dynamics. So, that corresponds to an NVE ensemble. So, this is my canonical ensemble. Averages can be calculated at the end of the simulation by just summing over individual steps. So, now let us see the logic of the Monte Carlo simulation. So, I start with step 1, go to step 2, step 3, step n, do this entire simulation. To go from step 1 to step 2, I use what is called a transition probability. Okay. So, this is essentially a stochastic algorithm. The essential feature in this stochastic algorithm is that transition probability from step 1 to step 2. So, how do I calculate the transition probability? So, this is the strategy. You have an old configuration which is determined by these blue dots, and each of the particle I will move a little bit. I will move a little bit in different direction by random moves. How do I generate these random moves? Generate random numbers in the x and y and z directions and move that a little bit. So, you can either move all particles at a time or you can move only one particle at a time. So, once I move my particles, I have got a new configuration. So, V old is the potential energy of the old configuration, V new is the potential energy of the new configuration, that is V old is of this original dots and V new is the all the new positions. So, when I have two energies now, So, what is the strategy? If the new potential energy is less than the old potential energy, accept that move. Okay? So, whenever I have a new energy less than the old, that is an acceptable move. Now, if the new potential energy is greater than the old potential energy, do not reject that move. Okay? If you reject that move, that will not be correct, but accept that move with a given probability. So, how do you calculate whether to accept the new one or not? Okay? Accept the new particle, you take the ratio new potential energy by kT, e to the minus new potential energy by kT divided by e to the minus V old by kT. Okay? So, if this ratio has a certain value, the next slide will tell you how to accept or reject with this new move. So, this is the slide now. So, what I am going to do, this position I have moved it to a new position. When I have moved it to a new position, I have a new potential energy. So, I took this delta V is the difference in the potential energy. So, now if delta V is greater than 0, so that means, okay. So, look at this graph, whenever the new potential energy is less than the old potential energy, this ratio will be greater than 1. Okay? This ratio will be greater than 1. So, I will accept that move. So, whenever the new potential energy is less than the old potential energy, that ratio e to the minus delta V will be less than 1. So, whenever this ratio is less than 1, suppose it is at this point, obtain a new random number. When I obtain a new random number, if that random number is less than this red line, accept the move. If the new random number is greater than this red line, reject the move. So, what this means physically is that if the new potential energy is very high compared to the old potential energy, then e to the minus delta V will be very small. So, very high energy configurations will be accepted with very low probability. Very low energy configurations will be accepted with high probability, and whenever the new potential energy is less than the present one, then it is certainly accepted. So, this is the strategy. So, energy configurations with very high energy are accepted with low probability, configurations with low energy are accepted with high probability. So, what it means is that the distribution function we get is exactly like a Boltzmann distribution. What is the meaning of a Boltzmann distribution? The Boltzmann distribution says probability is proportional to the e to the minus beta into energy. So, higher energy, lower probability, lower energy, higher probability. So, therefore, this particular strategy of Metropolis allows us to sample configuration based on a Maxwell-Boltzmann distribution. So, that is the meaning of this Metropolis Monte Carlo simulation. Okay. So, I have repeated the whole thing here. What are the selection criteria? I list them again. If the new energy is lower, more stable structure, then accept the move. If the new energy is higher, that is less stable, then generate a random number between 0 and 1, calculate Pij is equal to e to the minus Ej minus Ei, only accept the move if Pij is higher than the random number. If the random number is less than Pij, accept. If the random number is greater than Pij, then do not accept. So, this allows me, as I mentioned earlier, that the whole distribution you get will sample all the important configurations corresponding to a Boltzmann distribution. So, this is my Monte Carlo simulation. Now, let me summarize what I have done so far. I started with systems and examples of molecular dynamics. I considered the potentials. I considered the equations of motion. We discussed periodic boundary conditions. We need periodic boundary conditions because I want to simulate an infinite system. I want to simulate a liquid. So, you cannot simulate a liquid with 50 or 100 or 200 particles. It has to be much larger because liquids typically Avogadro number of particles. So, to have an infinite system, I use a periodic boundary condition. So, it not only removes the edge effects, it allows me to simulate a real liquid. So, minimum image convention, I only consider interaction of a central particle with all the remaining n minus 1 particles with this particle at the center. So, that is the minimum image convention. We considered in detail MD classical molecular dynamics simulations as well as Monte Carlo simulations. Okay. We discussed trajectories and averages. We discussed spatial correlation functions as well as time correlation functions, diffusion constant through mean square displacements, and what we will do, we will execute a program now of Monte Carlo as well as molecular dynamics. So, before I execute, I will tell you what is now the strategy of that program. So, that strategy of the program would be, the structure is, in the main program I read all the parameters like coordinates, velocities, I read in the main program, then calculate, then call a subroutine called Dynama. Dynama is the dynamic subroutine. So, what this subroutine does? It calculates other subroutines. What are them? ForeCal, calculate the force. Okay. Whirlay is a subroutine which gives me new positions and velocities. Okay. Then every few steps write the averages, and every step try to write position and velocities. So, that will complete my one step. Once I complete one step, I update my t to t plus delta t. Okay. So, this is done in the main program. Then if this new time is much greater than the maximum time, then stop. If it is less, I go back and keep on calculating my new positions and new velocities until you do from the starting time till the end time. So, starting time typically is 0 picosecond, ending time typically 50 or 100 nanoseconds. So, this is how we will do the simulation, and at the end of the simulation write files so that I can restart the calculation. So, next slide illustrates what are all these subroutines here. As I mentioned to you, Dynama, it controls the dynamics of the system, and it calls you ForeCal. ForeCal is the force calculation. This subroutine is to calculate temperature, and Whirlay is to calculate new positions and velocities. ForeCal, it does it calculates the potential energy as well as the force. Okay. Now, ACOMCOR, it checks the center of mass of the entire system. You know, as you keep on doing the simulation, the entire simulation box should not start moving to the right and left. So, you make sure of that by correcting for the center of mass. Whirlay calculates you, Whirlay algorithm. So, whenever a particle goes outside the box, you bring it back for the periodic boundary condition. AVSD calculates you averages, pair CF calculates pair correlation function. This VMD write, it writes the configuration for a VMD program. Gauss is a subroutine to calculate Gaussian random numbers. Okay. This one is for normal random numbers. There is a function random number generator also. Then what about the files for data files? NCORD or NCORD 0 contains all the initial positions as well as certain parameters. Okay. So, there are certain parameters to decide whether to start from a fixed configuration or to start from a previous configuration. ARGOUT, it gives you several outputs. BinDat gives you a restart configuration. GRDat is for pair distribution function. Positions are to calculate mean square displacement. Velocities are for time correlation function, and these other things are to check for errors in the program. Okay. So, now let us see how to run this program. So, the data file is contained in file NCORD. So, this NCORD has 3 data and the position. So, first line will tell me whether I will restart from a frozen configuration or restart from a old configuration. So, this is the restart option. So, the next one will be temperature, delta T, charge, box length, delta R for calculating GFR, and then Q1 is an initial random number. So, these are all the variables I will show you in the program. Then finally, it reads all the coordinates and velocities. So, what I will do now, I will actually shift to the program, execute Monte Carlo as well as molecular dynamics, and then conclude this part of my lecture. I am now going to demonstrate execution of the molecular dynamics as well as the Monte Carlo program. All my files are in this directory MCMD. Okay, so, let me just do ls. So, when I do ls, you get a list of all the files. You see, you have which are my files. Okay, let me do ls minus l. Okay, my argon.f is my molecular dynamics program. Argon.mc.f is my Monte Carlo program. Then MSD.f calculates me mean square displacements, and VACF.f calculates me velocity autocorrelation function. So, what I will do, I will illustrate first the molecular dynamics program. So, how do I do that? I compile G-Fortran, argon.f, that is my molecular dynamics program. So, it has compiled now. So, let me see all the data is in NCORD. So, let me see VINC. Okay. So, this is my data. The first one is a restart option I discussed in the earlier class, and this one is to read the data. Then next I have this 10 tells me sub averages, how many sub averages I have. The next one is the number of steps. This is the number of particles 64. Okay. I am not okay. 64 is the number of particles and 75 is how many boxes I put my GFR. See, I want to calculate GFR. There are 75 boxes, that is 7.5 angstrom. Each bin for GFR is 0.1 angstrom. Then temperature is 190. This is my temperature. 0.01 picosecond is my time step. Okay. Then third one is a charge. Our system has no charge, so I put 0. Then 14.564 is the box length. 0.1 is the spacing for GFR, and 0.12345 is a random number. And then the next 64 lines, since there are 64 particles, there are 64 positions. These positions are all lattice positions now. Okay. So, now
can we start from any random number?
You can start with any random number. Main thing is you should every time you should change the random number, because if you keep the same random number you will get the same sequence. So, good programming wants to change it to some other number, and we know that when you start with a given random number, to get the same random number it takes a very long time. Okay. So, the algorithm is such that the random numbers will not repeat for at least several lakh steps. So, even if you give the same random number, it will not be too bad, but it is not a good thing. Always change the random number, so that ultimately you want to have a different configuration. Your Monte Carlo should have, it should span the whole space, always it should be different. Okay. So, now, so I will run that MD program now. So, A dot out. So, now it is saying, okay. So, I made a mistake, dot slash I did not give, dot slash. So, now it is doing all these calculations, it will do for 10,000 steps. Okay. So, when it does 10,000 steps, it will stop my, okay. So, when it has done the 10,000 steps, so I can see that. So, this is my output file. So, what does this output file contain? My initial data, whatever I fed in, initial data, okay. Then initial, okay, I am not able to see it, okay. Okay. The output file contains this ARGOUT, all the initial data I fed. This is from a cold start because restart was 0. Okay. Then I calculate velocities from a random distribution, okay, at temperature T. So, this is my root mean square velocity from the Gaussian distribution. Then it writes all the initial velocities for a cold start, it writes the initial velocities, okay. It writes all the initial velocities, there are 64 of them. Then it will temperature, it lists all the forces, on each of the atom, okay. Then it calculates the temperature in every sub average, okay. Every 10 steps it is calculating the temperature. So, it is listing the temperature for the entire simulation. There will be 10,000 steps. So, I am going to write every 10 steps. So, it will write 1000 times.
But here we are not doing anything to keep the temperature constant.
No, there is a rescaling. We rescale temperature every few steps. That is already there. Okay. So, we rescale every step, every few steps. So, now these are my averages during the simulation. These are the final averages over the entire sample. So, you can go to the program, you will see that the first one will be the average potential energy, okay. Second one will be the temperature, third one will be kinetic energy. So, all the averages are calculated during the simulation, and finally, this is my final configuration, final forces, okay. These are my final forces, then final positions, okay, then final velocities, okay. So, and this is the random number. So, now I come out of this, okay. So, if I want to restart from this configuration. If I want to restart from this configuration, I change my n coord. So, okay, there is, I made a wrong statement. I will come out V I N C O O R D. So, what I do here, I change the first 0 to 1. You are not able to see that. Okay. I change, let me show that. So, the first one was 0 for a cold start. Now, I will replace it with 1. Okay. So, I have replaced that. Now, I will run a dot out again, dot slash. So, this time when I run, it is running from the last configuration of the last simulation. When I did 10,000 steps, so remember in Verlet I need present step and the old step, correct. So, what it is writing in that file bin dat, it will write the old position, current position and the current velocity. So, for a restart, I use bin dat file which has current position, past position and velocity. So, then I can do Verlet, no. For Verlet I need V new is equal to 2 times V current minus V old. So, that is the MD run. Now, I want to calculate velocity autocorrelation function. So, what I will do, let me compile that program. G Fortran VACF dot F. So, I compile the velocity autocorrelation program. Now, I do dot slash a dot out. So, this program uses all the velocities. Look at this line, see it writes all the velocities. Can you see these velocities here? Yes. That velocities has all the velocities for 10,000 steps. Positions will have all the positions for 10,000 steps. So, I can execute. Now, it has already completed. So, let us see. So, I did VACF. So, VACF dot out will have the output for the velocity autocorrelation function. So, let me edit that VACF dot. So, these are all the my velocity autocorrelation functions. Remember 0.1 this is the value, 0.3 this is the value. So, as the time increases to around 0.39 it has taken a negative value. Remember we had shown a plot of autocorrelation function, it starts with 1, goes to a negative value, comes up again and finally goes to 0. So, this is my velocity autocorrelation function program. So, finally see it has gone to 0 at about 2 picoseconds. It has gone to 0 and it also calculates a diffusion constant using that relation integral, this is the diffusion constant. So, now I can also do mean square displacement. How do I do that? G Fortran So, I am compiling the mean square displacement program. So, it will calculate mean square displacement as a function of time. So, just as in the earlier case I had a plot of velocity autocorrelation versus time. Now, I will have a mean square displacement versus time. Once this program is over, I will tell you how it calculates the mean square displacement. Okay. So, the what was that file now? MSD.out. You see that MSD.out? So, I edit that file VI. So, at each time step it is calculating the mean square displacement. So, if I plot this mean square displacement versus time, I can take the slope and calculate the diffusion constant. So, remember that the mean square displacement becomes 6 dt at large times. So, this is how you can calculate the mean square displacement by plotting this mean square displacement versus time. And I would also urge you to look at a software called XMGrace. XMGrace allows you to take a file from your data and plot on your screen. Otherwise, you will have to take the Scilab. You can plot in Scilab, no? Yes. You can take all this in Scilab and plot, or you can plot using XM Grace software. So, the last program I will illustrate now is Monte Carlo program. So, for that I will compile the Monte Carlo program. G Fortran, I am compiling the Monte Carlo program. Okay. So, I have combined the Monte Carlo program. So, in the Monte Carlo program there is no time. So, what we do, since there is no time, so in my old program this 0.01 was delta t. So, now this delta t is the displacement in Monte Carlo. So, what I will do, I will change it to instead of 0.01 I want 0.1. Okay. How do I delete that? So, I have made 0.1. So, I have added escape. So, I have added 0.1 as the maximum displacement in each step, 0.1 angstrom. So, no particle will move more than 0.1 angstrom. So, I will escape. Did I compile the Monte Carlo? Now, let us see again. So, it is all right. So, I escape. I have compiled Argon MC, I have compiled. Now, let me execute /a. So, now it is doing this Monte Carlo calculation for 10,000 steps. So, this will take a very long time. So, should we do it for smaller steps so that we can demonstrate quickly?
Yes, sir.
So, I can stop it by saying Control Z. This has stopped. So, what I will do, instead of 10,000 steps, I will just do for 100 steps. Okay. So, this is mainly to illustrate. So, since it is going to do 100 steps, it will be over very quickly. So, what we are doing here, we are executing the Monte Carlo program, not the molecular dynamics. Okay. So, this will be over very shortly. So, it will be 100 into 10, so 1000 steps, and in Monte Carlo simulation it will not calculate for you any velocities, it will only calculate new positions. No forces are calculated because nothing moves because of a force, it is just a random movement. So, at the end of this you will see that ARGOUT will have output file which has only the final configuration, the velocities have no meaning. Okay. So, what I urge you now, since we have used these different programs, look through the program and check all the names of subroutines. So, check all the names of subroutines. So, the name will tell you, FORCAL will calculate forces, Verlet will calculate positions, MC will calculate MC steps using random numbers. So, that allows you, and look at all the read and write statements, what files are written to, what files are read from, and once you know this, you will get a good feel for all these programs. Okay. So, it should stop at 100. So, I will just edit. Okay. So, I wrote a wrong thing. So, this is the output of the Monte Carlo. So, you see that 0.1 was the spacing, that 0.1 is given here. This is my initial cold start. Okay.
Again, it's showing cold start. Why?
Because when I do Monte Carlo, see what I have done, I have used the old program only, I have not changed anything. Instead of a FORCAL, I have a MC. All the rest, so what I will do, I will change all the unnecessary things and just make it a Monte Carlo program. See, you will see that whenever you write a new program, you want to start from an old one, correct? It is like when you move to a new room from an old room, you carry all the old things from the old room. So, this program is a MD program where the force is removed. In place of forces, I calculate Monte Carlo moves. Okay. So, in assignments, we will give you many exercises where you can run this program for other situations. Now, what do you think you will do? Suppose you want to, instead of argon, you want to do krypton. What will you do?
We have to change the temperature.
No, I want to do at the same temperature. How will you do?
Change the coordinates.
Coordinates will change, but you have to change the parameters, no? If argon has sigma of 3.4, krypton will have a parameter of 4.0. So, if you change the Lennard-Jones parameters, you will get the krypton. Okay? So, you can do for many systems now. So, what I will urge you, you look at all the subroutines, look at all the read and write files and execute it for different situations. Okay? So, from next time onwards, we will use a GROMACS program which is far more elaborate, but through this MD program you will know what each step in your MD means. Okay? It is always good to know every step in a program. A good programmer knows every line in his program, whereas a average programmer takes someone else's program and runs it. Okay? So, hope you will enjoy, and we will continue with GROMACS simulations in the next lecture. Thank you.